Bismillahirrahmanirrahim. Welcome to Easy Learn, and today we are going to discuss the transmission system because in the previous episodes we discussed the generation side where we discussed let's first open the discussion where, for example, this is the generators which from where we can obtain our three-phase system. A three-phase power system can be generated at a high voltage level if the powerful generators, definitely to ensure that we have to power so many consumers requirements. We have to meet all the consumers needs, so the generators must be powering at least 20 kV for the high power generating stations. If we can rotate by a strong prime mover, if it is a hydropower, definitely from the power of the water, falling water, gravity, and if it is a steam power station, then according to the steam, and it depends upon us. But right now suppose power is generated because we already discussed, and now the issue is the generating station are basically, suppose it is a hydropower station. So hydropower station means the dams. So dams is built where the suitable water reservoir is available, so it is not very close or near to the users ends mostly. So consumers or users are here, and there is a big distance and a big gap between the users and the generation side, where we have to transmit the electricity through this with the help of the wires, not with the wireless transmission. Right now wireless transmission is nowadays is a research project and they are working on it, but this is with the help of the wires possible to transmit the power. We need to consider wires, and we are going to discuss this how we can transmit. There are the two main challenges. Number one is definitely cost. So cost definitely matters because we have to transmit the network system must be developed to transmit the electricity from generation to the user's end, and for that definitely a very high cost because this is the thousands of kilometers away, and not only like the simple wire that is used in the homes can be used, and a heavy wire can be used, and definitely. So this is the first major issue, and the second major issue is the power lost. We are facing another. If we develop this system, the power losses issues are also needs to be considered. Suppose if we are generating here, just for the sake of an example, 100 volts are generated here. If we are receiving here 50 volts, this is useless because we are wasting half voltage is wasted in the way. So we have to be faced the challenge, this one, that is the second case, and the first also, the initial cost for the transmission system. Actually power is the multiple of the voltage and current, and we are mostly considering this formula, the loss factor, that is the I square R, or power loss is equals to I square R. Then how does it come from? It is actually from the Ohm's law that states that voltage is equals to current multiplied with the resistance of the conductor, or you simply say that voltage is directly proportional to the current, provided that the resistance is constant throughout the conductor across the terminals. So if we substitute V is equals to IR in this formula, IR in place of the V, and here is I multiplied by I, it is I square, and here it is R, and it is called power loss formula. Usually we use it for the losses. It is clear from this stage that the power losses is directly proportional to the square of the current, not only current but the square of the current. So if we can reduce the current by any way, so we can definitely manage to reduce the power losses in the transmission. So this is definitely a big challenge, and for doing so, because this is the alternating current, thank God we can use the transformers there, because transformer also works on the alternating current. So we can use the step up transformers at the generating side, step up by generation side, and step down at the user side, because users cannot handle such a high voltage. Because what step up do at the generating side, after the 20 kV, step up will definitely increase the voltage level, and by increasing the voltage level, automatically current will be reduced, because the overall result is the multiple of the power into power is equals to voltage multiplied by current. So current is automatically reduced. When current is reduced, our transmission definitely losses will be reduced, and again we will do the step down at the user's end. The equation P is equals to VI could be used, but the value for V that must be substituted in the equation is the potential across. Here remember that it doesn't mean that the power is equals to VI formula cannot be used. Why this formula can be used to determine the power losses? Definitely this can be used, but why we are changing this into this power loss is equals to I square R? Basically this is because we can easily manage this formula. I current can be easily calculated if it is a generating station and this is very far our user end. So if we want to calculate this formula, evaluate, we are suppose again considering the same formula, same scenario. If we are generating 100 volts and user is getting 50 volts, and we have potential is dropped half almost. In terms of the volts, we can say 50 volts are dropped, so the potential drop is 50 volt. We have to substitute the dropped potential. 50 volts is dropped, so put the 50 in this formula and current can be calculated, because this is the series transmission, and you know when something is transmitted in this series, definitely the current is the constant. If we measure the current here, definitely the current doesn't vary much. Current can be measured by ammeter connected in this series, but for the sake of the voltage, we have to connect one end here for the measuring voltage one end, and other at the user end. And you know this is the far away, and this is the thousands of kilometers sometimes, so we can't manage this. So better we can use this formula I square R to avoid this confusion. So that is the reason basically for the use of, because we want to use the wires, definitely wire matters. If we simple wire is used, it has a high resistance. So if we increase the cross-sectional area by wounding it again and again the same wire on it, making it having a more cross-sectional area, making a thicker wire of it, by doing so we can manage to increase the diameter of the wire, and by doing so the more I can manage the diameter of the wire, the lesser the resistance will be I have to face. So the resistance of the wire will be reduced, because the current can follow the can get the more chance to pass through with the multiple ways. For example, if this is the single wire, how can current can found difficult path to go through, and if current has multiple ways, definitely it's easy for the current to flow and resistance will be reduced. This is the zoom picture of the end, or a cross-sectional picture of the wire that is used in the transmission system. Aluminium basically are used in this system, that is cheaper, number one benefit, and lighter. So weight, I said, also matter, because we have to adjust many poles on the transmission side, and for the sake of the weight, if the weight is high, because this is used variety of the ways to manage the weight. First one is to handle it with the lighter conductor, like this one. We are managing it with the copper, as not copper, because copper has more weight as compared to aluminium. Aluminium is much lighter, so we are going to with aluminium. The second is by using more poles, and that is of course not a desired or a feasible option, because more poles means that cost is increased. That is not a feasible option, so we are not going with that. The most common conductor is in use transmission system, that the diagram you are seeing is ACSR, aluminum conductor, steel reinforced. It means this is called core. The center core is made up of the same aluminum. Again, aluminum wires are wounded on the core. Core basically is the center where the magnetic field is induced of the current. Definitely, if the current, from the first episode what I told you, if the current is flowing in the coil, the current is flowing through a wire, a magnetic field due to this current will be developed. And if the wire has a high cross-sectional area, it is easy to handle this magnetic field. And this magnetic field make sure that this magnetic field has no contact with the other wires also. This is another picture where we can use this carbon core inside the galvanized steel wires, or you can say aluminum wires. This is the modern picture and this is the older. This is used nowadays mostly, but still this is we are using this because it is not easy to replace all the system. It increases the cost as well to replace this. The benefit of this is it reduces the power losses. You can easily see that this has much easy to handle because it is a hollow from inside also, and magnetic field can be easily handled. This effect is called corona effect. The glow you will see in this diagram is not just for the lightning purpose. We are not happy to see that beautiful corona, beautiful glow. No, because this is the waste of the electricity in the form of the heat. We are basically lack of the conductor. If we are using the less conductor as it should be, then the corona will appear. Corona appears basically when the conductor size is less as compared to it should be. It should be much higher than compared to this. The current flowing suppose in a wire is 100 ampere and there is no corona, and recommended current is 100. If we exceed the limit or the more current is passing, then for example 200 ampere or 1000 amperes, then definitely conductor, we can easily see the conductor and insulating material. Between conductor and insulation, the corona effect, the glow at the nights usually, and when it appears basically a huge amount of power is lost. And also due to the corona, a magnetic field radiations develop, and it also affect the mobile phone signals when you go through, and this phenomena is happening. And when you see, you will notice that due to this magnetic field, our signals of the mobile phone sometimes may affect. Also the radio signals may have a great interference with this. So corona effect needs to be considered and needs to be reduced. Corona sometimes also happen when the two phase wires come closer to each other. For example, this wire is containing a very high voltages, and the other wire also is having this very high voltages in the transmission lines. Usually this happens in the transmission lines, that if they are both wires have their own magnetic field, both wires, due to the flow of the current. And if the wires, with the help of maybe just because of the storms or anything, maybe a strong wind is blown, and they two wires, the space between these two wires, the gap, that is actually air, that is insulating material between, that is isolating the two wires magnetic field, is breakdown, because they come into the contact of the both magnetic fields come into the contact of each other. Then the corona, basically glow, can be seen near to each other. For that purposes, that the wires not come closer to each other, spacers are used. Spacers basically reduce this effect. Bundle conductors, in which each space wire is made up of the bundle of the 2 or 4 conductors separated with the help of the spacers. You can easily see these spacers whenever you go through highways. You will notice the transmission lines are facing these spacers. They are usually installed just after some time, where there is a where there is a danger of that the wire may come closer of if anything happen like wind or anything. Also, the vibration can be seen in the wire sometimes, and to do this we need to add the weight sometime in the wire to reduce the unwanted vibration. This is due to the also magnetic field, strong magnetic field, because of the high voltages. And you also listen sometime the sound. If there is a silence, you will hear a strong sound of coming through the wires. To keep the current as small as possible, given the practical size of the conductor, it is necessary to use high voltage. If we are using the high voltage, there is a direct relation of the size of the conductor. I has a direct relation with the size of the conductor. Means if we are using the current is low, as in the high transmission lines our voltage is high, current is low, then the size of the conductor is also small size can be handled to manage the very high voltages. But if the current is low, if the current is high, it means that voltage is low, then we have to manage the same amount of the power for more amount of the conductor is necessary. A heavy conductor, the highest voltage used for transmission of electricity in Australia is 500 kilovolt. To insulate the line conductor from sporting structure, glass or porcelain insulators are used. The poles that are used to support the wires, to hang on the wires, there are the insulating conductors that provide the contact between the poles and the wires. And for the supporting structure, definitely must be have no electricity. They must have disconnect. So where we are using the special insulating material that is consists of the porcelain or sometimes glass. So both are used. Actually these wires are made up of as we discussed, the aluminium coating, aluminium cores inside also, and the outers are also aluminium combination, while due to their weight basically, and the cheap also. The copper wires are basically used for the grounding purposes and for the distribution, and sometimes they are costly as compared to this also. These can be seen holding the transmission wires away from the transmission towers. So this is the flow chart diagram where we can easily see that this is the power generation, where we are generating the power at 16.5 kilovolt, or simply you can say 20 kilovolt suppose, and we are just making a high transmission. Then with the help of the step up transformer, we increase the voltage level to 220 volt or 500 kilovolts. 500 kilovolt means 500,000 volts. Then transmitted it over to the terminal station, that is the first, where we are going to reduce it to 66 kilovolt for the sub transmission system. And this is just in the diagram looking very simple. Actually this is hundreds of the kilometers. And then 66 kilovolt to 11 kilovolt. And from here we also, why these are the uses? Basically these are used to cope and handle the problems that, for example, if the problem is in between them, so we cannot we can manage only between these two ends. We do not need any system to contact from here to here. It is a long distance, so different substations comes from the direct power station to the user's end. So this is the first one where we are going to reduce to 66 to 11 and 22 kilovolts maybe first if we can use 22, then maybe in the next substation we can reduce from 22 to 11 kilovolt. This can also be used to provide the direct connection to the industries according to their demands. And here you can see this is the AC to DC basically rectifier transformers, where we use to power the trams and trains, as we discussed in the previous episode, because they need a high direct current power to start the train engine from the ground and static position in the moving movement. Basically, initializing process need a high power, so for that DC current plays a vital role there. They are having a direct connection from 11 kilovolts. And then we have a cubic transformer, cubic and underground street mains and services. This is the distribution system, and this is also the distribution system towards the users, and where we are going to reduce the 11 kilovolts into the 415 for the 3-phase or 440 for the 3-phase to 220 to 40 for the user ends. Before this 11 kilovolt is reduced into 220, the system is called this is system that is used is called the transmission system. Then this one is the distribution system, and the before all the system is distribution system, while this is the transmission. So we are going to discuss further details in the coming episode, but before going to end the discussion, there is a question which I am going to leave for you so that you can easily understand and enhance your knowledge. 33 megawatt of the power with a voltage of 66 kilovolt arrives at a town substation from a generator over transmission lines that have a total resistance of 6 ohm. So this is the 33 megawatt of the power, actually power, and the voltage is given, that is 66 kV arrived at a substation. So total resistance of the line is also given. What is the current in the transmission line? Using the simple formulas you can easily calculate. I'm not giving here because this is the quiz question for you to solve out by yourself. You can ask for the help in the comment sections or on our Facebook page, where I will definitely try to help you. What I can do, I will try my best to answer your questions there. So this is the end of the episode 23. We will continue the discussion in the next episode. Take care. Allah Hafiz.